Preparing for AI search engineer interview? You've reached Candy Mentor, and this video is for you. We'll walk through 20 key questions you're likely to face. For each question you'll see a sample answer followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. How would you design an end-to-end AI search system? AI search combines information retrieval with machine learning to return useful results, not merely matching words. I would normalize documents, build lexical and semantic indexes, retrieve candidates with BM25 and vector similarity, then re-rank using learned relevance signals. I would evaluate retrieval quality and user satisfaction with recall at K, NDCG, and success rate. The key design choice is balancing precision, latency, freshness, and cost across every stage. While answering, cover ingestion, document processing, lexical and vector indexing, candidate retrieval, re-ranking, response generation, feedback loops, observability, latency targets, and evaluation metrics. Question 2. When would you choose BM25, vector search, or a hybrid approach? BM25 is strong for exact terms, identifiers, and rare keywords, while vector search captures semantic similarity and paraphrases. For example, BM25 handles a product code better than an embedding model, whereas vectors understand that reset credentials relates to forgot password. I typically use hybrid retrieval, combining normalized lexical and dense scores, then re-ranking candidates. That approach improves recall, but adds indexing, tuning, and operational complexity. Make sure to cover exact match behavior, semantic similarity, vocabulary mismatch, sparse and dense representations, recall, precision, explainability, latency, and why production systems often combine retrieval methods. Question 3. How do you select and evaluate an embedding model for semantic search? I select embeddings based on retrieval performance for the target domain, languages, query types, and operational constraints. I build a labeled dataset containing positive documents and hard negatives, then compare models using recall at K, MRR, and NDCG. I also measure embedding latency, memory, and indexing cost. A larger model is not automatically better. Domain-specific evaluation and representative production traffic determine the practical choice. In your answer, discuss domain fit, multilingual coverage, embedding dimension, similarity behavior, benchmark design, hard negatives, latency, cost, model drift, and offline versus online evaluation. Question 4. How would you implement hybrid search and combine lexical and vector scores? I would retrieve separate candidate sets from BM25 and an approximate nearest neighbor index, deduplicate them, and combine rankings. Reciprocal rank fusion is a robust starting point because it avoids incompatible raw score scales. If labeled data exists, I would learn query-dependent weights or use a reranker. I would test rare terms, long natural language queries, and ambiguous queries separately, because one fixed blend can hide meaningful weaknesses. Be sure to mention independent candidate generation, score normalization, reciprocal rank fusion, learned weighting, query-dependent behavior, duplicate handling, and offline experiments before choosing a production strategy. Question 5. How do chunking strategy and metadata affect retrieval quality in a RAG search system? Chunking determines whether a retrieved passage contains enough context to answer a question without adding distracting text. I prefer structure-aware chunks based on headings, paragraphs, tables, or code blocks, with limited overlap. I preserve metadata such as source, permissions, timestamp, and section title. For long documents, parent-child retrieval can search small chunks but return their surrounding section. I validate choices using retrieval and grounded answer metrics. Focus on semantic boundaries, chunk size and overlap, parent-child retrieval, metadata filters, document structure, citations, context limits, and experiments that connect chunking choices to recall and answer quality. Question 6. How would you handle query understanding, rewriting, and expansion? I first classify intent and identify entities, filters, language, and conversational references. Then I may correct spelling, expand acronyms, or generate alternate queries for ambiguous wording. In conversational search, rewriting should resolve context while preserving the user's intent. I would retain the original query for fallback and auditing, apply confidence thresholds, and avoid aggressive expansion when precision matters. Every rewrite should be evaluated against the original. Discuss spelling correction, intent classification, entity extraction, conversational context, synonyms, query decomposition, generated query risks, latency budgets, and safeguards against changing the user's original intent. Question 7. What role does a reranker play, and how would you design one? A reranker improves ordering after inexpensive retrieval has produced a manageable candidate set. I might use a cross-encoder that jointly reads the query and document, because it models interactions more accurately than independent embeddings. Training can use clicks, judgments, or pairwise preferences, with careful debugging. I would cap candidates to protect latency, cache frequent requests, and fall back to first-stage scores during failures. Mention first-stage recall, cross-encoders, listwise or pairwise learning, feature design, candidate limits, latency, training labels, calibration, and fallback behavior when the reranker is unavailable. Question 8. How do approximate nearest neighbor indexes work, and how would you tune them? Approximate nearest neighbor indexes trade a small amount of recall for much lower search cost. HNSW builds a navigable graph, while IVF partitions vectors into clusters and searches selected partitions. I tune parameters such as HNSW search depth or IVF probe count against recall at k, latency percentiles, memory, and build time. I benchmark realistic traffic, because synthetic random vectors often misrepresent clustered queries and filtering behavior. Cover HNSW or IVF, recall latency trade-offs, index construction, search parameters, memory usage, filtering effects, benchmarking methodology, and the importance of tuning against real query distributions. Question 9. How do you support metadata filtering in vector search without destroying recall or latency? Filtering can happen before vector search, during traversal, or after candidates are retrieved. Post-filtering is simple but can return too few results when filters are selective. Pre-filtering improves correctness but may increase search cost or require specialized index support. I would inspect filter selectivity, overfetch candidates when safe, and use tenant-aware partitions where appropriate. Tests must include restrictive and compound filters, not only unfiltered queries. Explain pre-filtering and post-filtering, filter selectivity, filtered index structures, tenant isolation, candidate overfetching, fallback strategies, and tests for restrictive, common, and compound filters. Question 10. How would you design an indexing pipeline that keeps AI search results fresh? I would use an event-driven pipeline that captures creates, updates, and deletes, then processes documents through parsing, enrichment, embedding, and index publication. Events need stable identifiers, versions, retries, and idempotent consumers. I would support backfills and maintain metrics for ingestion lag and failed documents. New indexes can be built in parallel and swapped atomically. Deletions and permission changes deserve priority because stale access is a security issue. Talk about event-driven ingestion, parsing, enrichment, idempotency, versioning, deletions, retries, backfills, dual indexes, freshness SLAs, and consistency between source of truth permissions and searchable content. Question 11. Which metrics would you use to evaluate an AI search engine? Offline, I use recall at K to measure candidate coverage, MRR for the first relevant result, and NDCG for graded ranking quality. For generated answers, I add citation correctness, groundedness, and answer completeness. Online, I monitor successful sessions, reformulation, abandonment, zero result rate, and latency percentiles. Clicks are useful but biased, so I combine them with judged data, interleaving, and carefully designed A/B tests. Include recall at K, precision at K, MRR, NDCG, zero result rate, abandonment, reformulation, click bias, answer groundedness, latency percentiles, and online experimentation practices. Question 12. How would you reduce hallucinations in a retrieval-augmented generation search experience? I reduce hallucinations by improving retrieval first and making the model answer only from trusted, relevant context. I would re-rank passages, remove redundant chunks, preserve citations, and detect when evidence is insufficient. The prompt should require explicit uncertainty or abstention rather than invented details. I would evaluate citation entailment and answer faithfulness separately from fluency. A short, well-supported response is better than a confident unsupported one. Mention high recall retrieval, re-ranking, context limits, source citations, answerability detection, constrained prompting, confidence signals, abstention, and evaluation for faithfulness rather than fluency alone. Question 13. How should personalization work in AI search while protecting privacy? Personalization should improve relevance using permitted signals such as location, role, language, or explicit preferences, not silently expose sensitive history. I would enforce authorization before retrieval, minimize retained behavioral data, and provide controls to disable or inspect personalization. A ranking layer can blend global relevance with user context, with a strong global fallback for cold starts. Privacy review, audit logs, and tenant isolation are mandatory. Discuss explicit preferences, behavioral signals, consent, data minimization, access control, tenant boundaries, anonymization, explainability, cold start, and avoiding personalization that creates unfair or narrow results. Question 14. How would you meet strict latency and scale requirements for AI search? I would create an explicit latency budget for query understanding, retrieval, re-ranking, and generation, then run independent retrieval paths in parallel. AN indexes, embedding caches, re-ranker limits, and response caching reduce work. I would track P50, P95, and P99 rather than averages, because tail latency determines user experience. Under load, the system should degrade gracefully by skipping expensive generation or re-ranking instead of timing out. Cover request budgets, parallel retrieval, caching, approximate indexes, batching, model selection, streaming, autoscaling, tail latency, graceful degradation, and capacity planning based on realistic traffic patterns. Question 15. How would you build search over multimodal content such as text, images, and PDFs? I would extract text, layout, tables, and images from each asset, preserving page and section relationships. OCR handles scanned documents, while modality-specific encoders represent images and text. A shared embedding space enables cross-modal retrieval. Results should expose the original page or image for verification. I would rank by query modality compatibility and validate OCR-heavy, diagram-heavy, and multilingual cases separately, because one benchmark can hide major failures. Mention OCR, layout parsing, modality-specific embeddings, shared embedding spaces, modality-aware ranking, captions, table extraction, metadata, evaluation coverage, and graceful handling of low-quality content. Question 16. How can user feedback improve search ranking without amplifying bias? Clicks and dwell time provide valuable signals, but prominent results receive more attention simply because they appear first. I would combine implicit feedback with editorial judgments, randomization or interleaving, and position bias correction. Exploration helps discover alternatives, while spam and repeated click detection protects training data. I would monitor relevance across query segments and user groups, because optimizing aggregate engagement can worsen quality for less frequent or specialized searches. Discuss clicks, skips, dwell time, explicit judgments, position bias, exploration, counterfactual learning, spam resistance, feedback loops, and monitoring performance across queries and user groups. Question 17. How would you handle ambiguous or underspecified search queries? For an ambiguous query, I would identify plausible intents and either show diverse results or ask a targeted clarification question. For example, Apple support could mean a company, a device, or technical assistance. I would use session context and user permissions, but avoid overconfident personalization. Clarification is worthwhile when interpretations lead to very different actions. Otherwise, diversified results with visible categories reduce friction and preserve speed. Cover intent uncertainty, clarification questions, multiple interpretations, result diversity, query context, confidence thresholds, safe defaults, and measuring whether clarification improves task completion. Question 18. A search release improves offline NDCG but users report worse results. How would you debug it? I would first compare online and offline query distributions, then segment results by intent, language, freshness, traffic source, and user type. I would verify that labels contain no leakage and that NDCG reflects current user goals. Next, I would inspect zero result rate, reformulations, latency, and representative failed sessions. If quality is clearly degraded, I would roll back or shadow the release while isolating whether retrieval, ranking, or presentation changed. Explain segment analysis, data leakage checks, metric alignment, query distribution shifts, online logs, latency effects, index freshness, click bias, and rollback or shadow testing. Question 19. What security risks are specific to AI-powered search, and how would you mitigate them? The system must enforce document authorization before content reaches retrieval or generation. Filtering after generation is unsafe. I would defend against prompt injection by treating retrieved text as untrusted data, separating instructions, and validating tool actions. Ingestion should scan for poisoned or malicious content, while tenant isolation prevents cross-customer leakage. Logging, redaction, rate limits, and adversarial tests help detect exfiltration, abuse, and unexpected model behavior. Mention authorization-aware retrieval, prompt injection, data exfiltration, poisoned documents, tenant isolation, output validation, auditability, secrets protection, and adversarial testing throughout the pipeline. Question 20. Design an AI search system for an enterprise knowledge base with strict permissions and citations. I would connect approved repositories, normalize documents, synchronize ACLs, and attach permissions to every indexed chunk. Queries would use hybrid retrieval with security filters applied before content is exposed, followed by reranking and grounded generation. Each answer would cite document titles, sections, and timestamps, with an abstention path when evidence is weak. I would monitor freshness, authorization failures, recall at K, citation accuracy, task completion, and P95 latency. Be sure to cover connectors, ACL synchronization, document parsing, hybrid retrieval, secure filtering, reranking, citation preservation, freshness, audit logs, failure handling, and measurable success criteria. If you are still with us, congratulations, you are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.